Sometimes integrals involving trigonometric functions can be evaluated by first of all using trigonometric identities to rewrite the integrand, that's the quantity we're trying to integrate, in an alternative form which is a bit more amenable to integration. Sometimes a trigonometric substitution is appropriate. Both of these techniques we look at in this unit. Before we start, I want to give you a couple of preliminary results which we will be using over and over again and which will be very important. And the first one is I want you to make sure that you know that the integral of the cosine of a constant times x with respect to x is equal to 1 over that constant multiplied by the sine of kx plus a constant of integration. That's a very important result. If you integrate a cosine, you get a sine, and if there's a constant in front of the x, that appears down here. We'll take that as read in all the examples which follow. Another important result is the integral of a sine. The integral of sine kx with respect to x is minus 1 over k cosine kx plus a constant. If we're integrating a sine, the result is minus a cosine, and the constant factor there appears out down here as well. So those two results, very important. You should have them at your fingertips, and we can call upon them whenever we want them in the rest of the video. We'll also want to call upon trigonometric identities. And I'm going to assume that you've seen a lot of trigonometric identities before. We have a table of trigonometric identities here, such as a table that you might have seen many times before. If you want this specific table, you'll find it in the printed notes accompanying the video. Why might we want to use trigonometric identities? Well, for example, we've just seen that we already know how to integrate the sine of a quantity and the cosine of a quantity. But suppose we want to integrate a sine multiplied by a cosine, or a cosine times a cosine, or a sine times a sine. We don't actually know how to do those integrals at the moment, but if we use trigonometric identities, we can rewrite these in terms of just single sine and cosine terms, which we can then integrate. Also, the trigonometric identities allow us to integrate powers of sines and cosines. You'll see that using these identities, we've got powers of cosine, powers of sine, and the identities allow us to write integrands in terms of cosines and sines of double angles. We know how to integrate these already using the results I've just reminded you of. So I'm going to assume that you've got a table like this at your fingertips, and we can call upon it whenever we need to. Okay, let's have a look at a first example. And the example that I'm going to look at is a definite integral, the integral from x is 0 to x is pi of the sine squared of x dx. So note in particular, we've got a power here. We're looking at the sine squared of x. What I'm going to do is go back to the table and look for an identity that will allow us to change the sine squared x into something else. Let me just flip back to the table of trigonometric identities. The identity that I'm going to use is this one. The cosine of 2a is 1 minus twice sine squared a. If you inspect this carefully, you'll see that this will enable us to change a sine squared into the cosine of a double angle. Let me write that down again. The cosine of 2a is equal to 1 minus twice sine squared a. First of all, I'm going to rearrange this to get sine squared on its own. If we add 2 sine squared a to both sides, then I can get it on this side. And if I subtract cosine 2a from both sides, I'll remove it from the left. Finally, if I divide both sides by 2, I'll be left with sine squared a. And this is the result that I want to use to help me to evaluate this integral. Because what it will allow me to do is it will allow me to change a quantity involving the square of a trig function into a quantity involving double angles. So let's use it in this case. The integral will become the integral from 0 to pi. Sine squared x, using this formula, will be 1 minus cosine twice x, all divided by 2, integrated with respect to x. I've taken out the factor a half here, and I'm left with the numerator 1 minus cosine 2x to be integrated with respect to x. This is straightforward to finish off. It's a definite integral, so I have square brackets. The integral of 1 with respect to x is simply x. And the integral of cosine 2x, we know from our preliminary work, is just going to be sine 2x divided by 2, with a minus sign there, and the limits are 0 and pi. We finish this off by first of all putting the upper limit in, so we want x replaced by pi here and pi here. The sine of 2 pi is 0. So when we put the upper limit in, we'll just get pi by substituting for x here. When we put the lower limit in, x being 0 will be 0 here, and sine of 0 here, which is 0. So both of those terms will become 0 when we put the lower limit in. And so we're just left with simply a half of pi, or pi by 2. And that's our first example of how we've used a trigonometric identity to rewrite an integrand involving powers of a trig function in terms of double angles, which we already know how to integrate. Let's have a look at another example. Suppose we want to integrate the sine of 3x multiplied by the cosine of 2x with respect to x. Now we already know how to integrate sines, we know how to integrate cosines, but we have a problem here because there's a product. These two terms are multiplied together, and we don't know how to proceed. What we do is look in our table of trigonometric identities for an example where we've got a sine multiplied by a cosine. Let's go back to the table. The first entry in our table involves a sine multiplied by a cosine. Let me write this formula down again. 2 sine A cosine B is equal to the sine of the sum of A and B added to the sine of the difference A minus B. And this is the identity that I will use in order to rewrite this integrand as two separate integrals. We identify the A as 3x, the b as 2x. The factor of 2 here isn't a problem. We can divide everything through by 2, so we lose it from this side. So our integral, what will it become? Well, the integral of sine 3x cosine 2x dx will become, we want the integral of the sine of the sum of a and b. Well, the sum of a and b will be 3x plus 2x, which is 5x. So we want the sine of 5x added to the sine of the difference of a and b. Well, a being 3x, b being 2x, a minus b will be 3x, subtract 2x, which is just 1x. So we want the sine of x, all divided by 2. And we want to integrate that with respect to x. So what have we done? We've used the trig identity to change the product of a sine and cosine into the sum of two separate sine terms, which we can integrate straight away. We can integrate that taking the factor of a half out. The integral of sine 5x will be minus the cosine of 5x divided by 5. and the integral of sine x will be just minus cosine x. And there'll be a constant of integration. And just to tidy it up at the end, we're going to have minus the half with the 5 at the bottom there will give you minus cosine 5x all divided by 10. And there's a half with this term here, so it's minus cosine x divided by 2, plus a constant of integration. And that's the solution of this problem. Let's explore the integral of products of sines and cosines a little bit further. And what I want to look at now is integrals of the form the integral of sine to the power mx multiplied by cosine to the power nx dx. We'll look at a whole family of integrals like this, but in particular, for the first example, I'm going to look at the case of what happens when m is an odd number. Whenever you have an integral like this, when m is odd, the following process will work. So let's look at a specific case. Supposing I want to integrate sine cubed x multiplied by cosine squared x dx. Notice that m is an odd number. M is 3. Now, there's a little trick here that we're going to do now, and it's the sort of trick that comes with practice and seeing lots of examples. What we're going to do is we're going to rewrite the sine cubed x in a slightly different form. We're going to recognise that sine cubed can be written as sine squared x multiplied by sine x. That's a little trick. The sine cubed can be written as sine squared times sine. So our integral can be written as sine squared x times sine x multiplied by cosine squared x dx. And then I'm going to pick a trigonometric identity involving sine squared to write it in terms of cosine squared. Let's find that identity. We have an identity here which says that sine squared of an angle plus cos squared of an angle is 1. If we rearrange this, we can write that sine squared of an angle is 1 minus the cosine squared of an angle. We'll use that. Sine squared of any angle is equal to 1 minus the cosine squared of any angle. We'll use that in here to change the sine squared x into terms involving cosine squared x. Let's see what happens. This integral will become the integral of, or sine squared x will become 1 minus cosine squared x. There's still the term sine x, and at the end we've still got cosine squared x. Now this is looking a bit complicated, but as we'll see, it's all going to come out in the wash. Let's remove the brackets here and see what we've got. There's a 1 multiplied by all this, sine x times cosine squared x. So that's just sine x times cosine squared x. We'll want to integrate that with respect to x. There's also cosine squared x multiplied by all this. Now the cosine squared x with this cosine squared x will give us a cosine to the power 4x. There's also the sine x, and we want to integrate that also with respect to x, and there was a minus sign in front, so that's going to go in there. So we've expanded the brackets here and written this as two separate integrals. Now, each of these integrals can be evaluated by making a substitution. If we make a substitution and let u equal cosine x, the differential du is du dx dx. Du dx, if we differentiate cosine x, we'll get minus the sine x. So we've got du is minus sine x dx. Now, look at what we've got when we make this substitution. The cosine squared x will become simply u squared, and sine x dx altogether can be written as a minus du. So this will become minus the integral of u squared du. What about this term? We've got cosine to the power 4. Cosine to the power 4x will be u to the power 4. And sine x dx is minus du. There's another minus sign here. So overall, we'll have plus the integral of u to the 4 du. Now, these are very, very simple integrals to finish. The integral of u squared is u cubed over 3. The integral of u to the 4 is u to the 5 over 5, plus a constant of integration. All we need to do to finish off is return to our original variables. Remember, u was cosine of x. So we'll finish off by writing minus 1/3. U being cosine x means that we've got cosine cubed x plus 1/5. U to the 5 will be cosine to the power 5x plus a constant of integration. And that's the solution to the problem that we started with. Let's stick with the same sort of family of integrals. So we're still sticking with the integral of sine to the power mx cosine to the power nx dx. And now I'm going to have a look at what happens in the case when m is an even number and n is an odd number. This method will always work when m is even and n is odd. Let's look at a specific case. Suppose we want to integrate the sine to the power 4x cosine cubed x dx. Notice that m, the power of sine, is now even. M is 4. And n, which is the power of cosine, is odd. N is 3. What I'm going to do is I'm going to use the identity that cosine squared of an angle is 1 minus sine squared of an angle. And you'll be able to lift that directly from the table we had at the beginning, which stated the very important and well-known result that cosine squared of an angle plus the sine squared of an angle is always equal to 1. What I'm going to do is I'm going to use this to rewrite the cosine term in here in terms of sines. First of all, I'm going to apply the little trick we had before and split the cosine term up like this. Cosine cubed, I'm going to write as cosine squared multiplied by cosine. So I've changed the cosine cubed to these two terms here. Now I can use the identity to change cosine squared x into terms involving sine squared. So the integral will become the integral of sine to the power 4x. Cosine squared x we can write as 1 minus sine squared x. And there's still this term cosine x here as well. And all that has to be integrated with respect to x. Let me remove the brackets here. When we remove the brackets, there'll be sine to the 4th x times 1, all multiplied by cosine x. There'll be sine to the 4th x multiplied by sine squared x, which is sine to the 6x, all multiplied by cosine x. And there's a minus sign in the middle. And we want to integrate all that with respect to x. Again, a simple substitution will allow us to finish this off. If we let u be sine x, so that du is cosine x dx, this will become immediately the integral of, well, sine to the 4th x. Sine to the 4th x will be u to the 4. The cosine x times the dx, cosine x dx becomes du. Subtract sine to the 6x will become u to the 6, and the cosine x dx is du. So what we've achieved are two very simple integrals that we can complete to finish the problem. The integral of u to the 4 is u to the 5 over 5. The integral of u to the 6 is u to the 7 over 7, plus a constant. And then just to finish off, we return to the original variables and replace the u with sine x, which will give us 1/5 sine x to the 5, or sine to the power 5x, minus 1/7 u to the 7 will be sine to the 7x, plus a constant of integration. So that's how we deal with integrals of this family in the case when m is an even number and when n is an odd number. Now, in the case when both m and n are even, you should try using the double angle formulas. Now, I'm not going to do an example of that because there isn't time in this video to do that, but there are examples in the exercises accompanying the video, and you should try those for yourself. I'm now going to look at some integrals for which a trigonometric substitution is appropriate. Suppose we want to evaluate this integral. The integral of 1 divided by 1 plus x squared with respect to x. Now, the trigonometric substitution that I want to use is this one. I want to let x be the tangent of a new variable, x equals tan theta. Why have I picked this particular substitution? Well, all will become clear in time, but I want to just look ahead a little bit. By letting x equal tan theta, what we'll have at the denominator down here is 1 plus tan squared theta. 1 plus x squared will become 1 plus tan squared. And we have an identity already which says that 1 plus tan squared of an angle is equal to the secant squared of the angle. That's an identity that we had on the table right at the beginning. So the idea is that by making this substitution, 1 plus tan squared can be replaced by a single term, secant squared, as we'll see. So let's progress with that substitution. If we let x be tan theta, the integral is going to become 1 divided by 1 plus x squared will become 1 plus tan squared theta. And we have to take care of the dx in an appropriate way. Now remember that dx is going to be given by dx d theta multiplied by d theta. dx d theta. We want to differentiate x's tan theta with respect to theta. Now the derivative of tan theta is the secant squared. So we get secant squared theta d theta. So this will allow us to change the dx in here to secant squared theta d theta over on the right. At this stage, I'm going to use the trigonometric identity, which says that 1 plus tan squared of an angle is equal to the secant squared of the angle. So in other words, all this quantity down here is just the secant squared of theta. And this is very nice now because this term here will cancel out with this term down in the denominator down there, and we're left purely with the integral of 1 with respect to theta. Very simple to finish. The integral of 1 with respect to theta is just theta plus a constant of integration. We want to return to our original variables. And if x was tan theta, then theta is the angle whose tangent is x. So theta is tan to the minus 1 of x plus a constant. And that's the problem finished. This is a very important standard result, that the integral of 1 over 1 plus x squared dx is equal to the inverse tan to the minus 1 of x plus a constant. That's a result that you'll see in all the standard tables of integrals, and it's a result that you'll need to call upon very frequently. And if you can't remember it, then at least you'll need to know that there is such a formula that exists, and you'll want to be able to look it up. I want to generalise this a little bit to look at the case when we deal with not just a 1 here, but a more general case of an arbitrary constant in there. So let's look at what happens if we have a situation like this. Suppose we want to integrate 1 over a squared plus x squared with respect to x, where a is a constant. This time, I'm going to make the substitution, let x be a tan theta. And we'll see why we've made that substitution in just a little while. With this substitution, x is a tan theta, the differential dx becomes a secant squared theta d theta. Let's put all this into this integral here. We'll have the integral of 1 over a squared plus an x squared will become a squared tan squared theta. The dx will become a sec squared theta d theta. Now what I can do now is I can take out a common factor of a squared from the denominator. Taking an a squared out from this term will leave me 1. Taking an a squared out from this term will leave me tan squared theta. And then still on the top I've got a sec squared theta d theta. We have the trig identity that 1 plus tan squared of any angle is sec squared of the angle. So I can use that identity in here to write the denominator as 1 over a squared, and the 1 plus tan squared becomes simply secant squared theta. We've still got an a secant squared theta in the numerator, and a lot of this is going to simplify and cancel now. The secant squared will go at the top and the bottom. One of the a's at the bottom will go with the a that's at the top, and we're left with the integral of 1 over a with respect to theta. Again, this is straightforward to finish. The integral of 1 over a is a constant with respect to theta, is just going to give me 1 over a theta plus a constant of integration. To return to the original variables, we've got to go back to our original substitution. If x is a tan theta, then we can write that x over a is tan theta. And in other words, that theta is the angle whose tangent is tan to the minus 1 of all this, x over a. That will enable me to write our final result as 1 over a tan to the minus 1 x over a plus a constant of integration. And this is another very important standard result, that the integral of 1 over a squared plus x squared with respect to x is 1 over a tan to the minus 1 of x over a plus a constant. And as before, that's a standard result that you'll see frequently in all the tables of integrals, and you'll need to call upon that in lots of situations when you're required to do integration. Okay, so now we've got the standard result that the integral of 1 over a squared plus x squared dx is equal to 1 over a tan to the minus 1 of x over a plus a constant of integration. Let's see how we might use this formula in a slightly different case. Suppose we have the integral of 1 divided by 4 plus 9x squared dx. Now this looks very similar to the standard formula we have here, except there's a slight problem. And the problem is that instead of 1x squared, which we have in the standard result, I've got 9x squared. What I'm going to do is I'm going to divide everything at the bottom by 9, take a factor of 9 out, so that we end up with just a 1x squared here. So what I'm going to do is I'm going to write the denominator like this. So I've taken a factor of 9 out. You'll see if we multiply the brackets again here, there's 9 times 4 over 9, which is just 4, and then 9 times the x squared. So I haven't changed anything, I've just taken a factor of 9 out. The point of doing that is that now I have a 1x squared here, which will match the formula I have there. If I take the 9 outside the integral, I'm left with 1 divided by 4/9 plus x squared, integrated with respect to x. And I hope you can see that this is exactly one of the standard forms now when we let a squared be 4 over 9. So if a squared is 4 over 9, we have the standard form. If a squared is 4 over 9, a will be 2 over 3. And we can complete this integration using the standard result. The 1 over 9 stays there. We want 1 over a. Well, a is 2/3, so we want 1 divided by 2/3. Tan to the minus 1 of x over a. X divided by a is x divided by 2/3, plus a constant of integration. Just to tidy these fractions up, 3 will divide into 9 3 times, so we'll have 3 2s are 6 in the denominator. Tan to the minus 1, and dividing by 2/3 is like multiplying by 3 over 2. So I'll have tan to the minus 1 of 3x over 2 plus the constant of integration. So the point here is you might have to do a bit of work on the integrand in order to be able to write it in the form of one of the standard results. Okay, let's have a look at another case where another integral to look at where a trigonometric substitution is appropriate. Suppose we want to find the integral of 1 over the square root of a squared minus x squared dx, where again a is a constant. The substitution that I'm going to make is this one. I'm going to write x equals a sine theta. If I do that, what will happen to my integral? Let's see. I'll have the integral of 1 over the square root. The a squared will stay the same, but the x squared will become a squared sine squared. A squared sine squared theta. Now, the reason I've done that is because in a minute I'm going to take out a factor of a squared, which will leave me 1 minus sine squared. And I do have an identity involving 1 minus sine squared, as we'll see. But just before we do that, let's substitute for the differential as well. If x is a sine theta, then dx will be a cosine theta d theta. So we'll have a cosine theta d theta for the differential dx. Let me take out the factor of a squared in the denominator. Taking an a squared from this first term will leave me 1, and an a squared from the second term will leave me 1 minus sine squared theta. And I have still got an a cos theta d theta at the top. Now let me remind you, there's a trig identity which says that the cosine squared of an angle plus the sine squared of an angle is always 1. So if we have 1 minus the sine squared of an angle, we can replace it with cosine squared. So 1 minus sine squared theta we can replace with simply cosine squared theta. There's the a squared out the front here, and we want the square root of the whole lot. Now, this is very simple. We want the square root of a squared cosine squared theta. If we square root these squared terms, we'll be just left with a cosine theta in the denominator, and with an a cosine theta in the numerator. And these will clearly cancel out. And we're left with the integral of 1 with respect to theta, which is just theta plus a constant of integration. Just to return to the original variables, given that x was a sine theta, then clearly x over a is sine theta. So theta is the angle whose sine is, or sine to the minus 1, of x over a. So replacing the theta with sine to the minus 1 of x over a, we'll get this result. And this is a very important standard result, that if you want to integrate 1 divided by the square root of a squared minus x squared, the result is the inverse sine, or the sine to the minus 1, of x over a plus a constant of integration. We'll have a look at one final example, which is a variant on the previous example. Suppose we want to integrate 1 divided by the square root of 4 minus 9x squared dx. Now that's very similar to the one we've just looked at. Remember that we had the result that the integral of 1 over the square root of a squared minus x squared dx was the inverse sine of x over a plus a constant. Keep that in mind. That's the standard result we've already proved. We're almost there in this case. The problem is that instead of a single x squared, we've got 9x squared. So like we did in the other example, I'm going to take the factor of 9 out to leave us just a single x squared in there. And I do that like this. Taking a 9 out from these terms here, I'll have 4 ninths minus x squared. Again, the 9 times the 4 ninths leaves the 4, which we had originally, and then we've got the 9x squared, which we have there. The whole point of doing that is that then I'm going to extract the root 9, which is 3, and bring it right outside. And inside, under the integral sign, I'll be left with 1 over the square root of 4 ninths minus x squared dx. Now in this form, I hope you can spot that we can use the standard result immediately. With the standard result with a squared being equal to 4 ninths, in other words, a being equal to 2/3. So putting all that together, we'll have a third, that's the third, and the integral will become the inverse sine of x divided by a. A was 2/3. Plus a constant of integration. And just to tidy that up, we'll be left with a third inverse sine. Dividing by 2/3 is the same as multiplying by 3 over 2. So we'll have 3x over 2 plus a constant of integration. And that's our final result. So we've seen a lot of examples there of integration using trigonometric identities and integration using trig substitutions. You need a lot of practice, and there are a lot of exercises in the accompanying text.